In this class, we study Work-Kinetic-Energy Theorem. Work-Kinetic-Energy Theorem was constructed by Coriolis. The famous for his Coriolis force, that is non-inertial reference, not that is inertial force, that is fictitious force measured in a non-inertial reference frame, such as on the surface of the Earth that is rotating about the axis of the Earth. If the wind blows, the direction of the wind deviates to the right on the northern hemisphere because the Earth is rotating counterclockwise seen from above the North Pole. By the way, the work-kinetic energy theorem has not been developed by a single person called Coriolis. It has a long history. The Newton and Descartes, they knew about something about mechanics, and Newton has been successful in constructing universal gravity and the three laws of equation motion, Newton's law of motion. However, it was not enough. The energy concept has not been developed yet. So, for example, the collision of billiard ball based on the elastic collision was not completely solved at the time of Newton and Descartes. However, Leibniz introduced an interesting idea called Bispeba, and actually he introduced for the first time of the kinetic energy concept. The only thing he missed over a factor of 1/2, and that was corrected by Émile du Châtelet, who translated Newton's Principia into a French version. So after that, understanding the kinetic energy completely, the Coriolis summarized this theory as a work-kinetic-energy theorem. And then the conservative force was completely understood, and in combination with the work-kinetic-energy theorem, the concept of conservative force is combined to finalize the theory to construct the conservation of total mechanical energy. And then the energy concept was further developed by the Lagrange and Hamilton. And nowadays we use the Euler-Lagrange approach for rewriting the equation in a more abstract way. That is, the Euler-Lagrange equation is equivalent to the Newton's equation of motion. And then it is further developed to express the second order linear differential equation as an equation of motion into coupled single derivative equations that is called Hamilton's equations. Anyway, work-kinetic energy theorem is a gateway to go ahead with a more abstract theory of Newtonian mechanics. So let us first consider Newton's law of motion. In non-relativistic theory, this F equals ma can be expressed in terms of first of all the time derivative of linear momentum. And linear momentum is the product of mass and velocity. In non-relativistic theory, time dependence of mass vanishes. However, we shall find that the mass is not independent of time. Mass depends on velocity Hence, this one is not equals to 0. The actual value is rest mass divided by 1 minus x dot square over c squared. This over factor is called the Lorentz factor. So this confronts with the Galilean relativity. Galilean relativity assumes time is always the same for any observer in any inertial reference frame. Mass of particle is also invariant under Galilean transformation. However, this one is broken, and this formula is the direct consequence of the time dilation. Therefore, F equals ma style does not work at all. However, fortunately, this modification, this is equivalent in the non-relativistic theory. However, in the relativistic theory, only this expression is correct, and this ma style is not correctly representing the force. So we would like to stress the point that force only in the non-relativistic theory, F equals ma. In general, force is linear momentum's first order time derivative. Let us go further with this expression. In the non-relativistic theory, first, is mx double dot equals f. We have x double dot. Why don't we replace this one with v dot? Then x single dot is v. So we have mv dot equals f. We multiply velocity as a scalar product. Here we find this is the, if we recall the Leibniz rule, this is the Leibniz rule, then we can express this one as a single time derivative of v squared up to over a factor of 1/2 that Leibniz missed to find the kinetic energy. Leibniz b by is mv squared instead of 1/2 mv squared. Unfortunately, even though Leibniz introduced the Leibniz rule, then m v dot v equals f dot v, and this one is 1/2 m v squared time derivative. Let me move this dt to the right hand side. Differential of 1/2 mv squared equals f v dot dt, and v dot dt, v dt equals dx, differential of position. So this differential displacement. That's it. This is Work-Kinetic-Energy Theorem. If you integrate both sides, what you obtain is a change in the 1/2 mv squared, and that is integral of this one. Let us call this one as a work. And this is called Work-Kinetic-Energy Theorem. What we have made use of was the square time derivative is a chain rule to v dot, right? This was based on this formula, Leibniz rule, extension of the Leibniz rule. And why don't we make use of Cartesian application, express the vector in terms of Cartesian coordinates, and make use of orthogonality of Cartesian basis vector that is chronic delta, that is either 1 or 0. If I equals j, then it's 1. If I is not equal to j, then it's vanished. Then the scalar product becomes a1 b1, a2 b2, a3 b3. That is, the matrix representation is created. This should be the origin of the matrix algebra. Then we apply Leibniz rule for the product function. Take the derivative, first one, the second one, and add them up. But we can find this one can be expressed as a dt, dA, dt, dA, dt, b1, b2, b3. So that is the scalar product of this in such a manner. The second three terms, like the last three terms, can be combined in this way, and replacing this Leibniz style as Newton style, a dot b plus a b dot, and then substituting b equals to a, we find this one that can be obtained by chain rule. And then the x8 is replaced with velocity. Then we end up with this representation. And finally, we have obtained this formulation that is the crucial point of the Coriolis Work-Kinetic-Energy Theorem. So this one we call the kinetic energy. Later, we study U, that is a potential energy. So kinetic energy plus potential energy is called total mechanical energy. That is also called H, that is Hamiltonian. If you study further on classical mechanics, T minus U, kinetic energy minus potential energy, is Lagrangian. And from Lagrangian, we can derive the equation F equals ma. So kinetic energy, especially the non-relativistic particles' kinetic energy is 1/2 mv squared. There's another way to express the 1/2 mv squared in terms of conjugate momentum. In classical mechanics, there is a coordinate, and first order time derivative of coordinate is called velocity, and mass multiplied by the velocity is called p. That is a linear momentum. And actually, there is a coordinate and there is a linear moment. But coordinate can also be chosen as an angle if in case we have a rotation. This is coordinate. And coordinate has its own time derivative is velocity, but it is rotating and it is not dimension. It does not have a length of dimension, then dimension of length. So we say it is an angular velocity. And there is a mass, but here we have a rotational mass. Rotational mass or rotational inertia. Mass is inertia. So rotational inertia. This is the momentum, but this is due to the rotation. So we say it is an angular momentum. In these two cases, we say coordinate, and then P or angular momentum is usually written as L, P or L. The theta to the L, X to the P, we say they are always a pair. They make a pair, and this pair is called conjugate. Conjugate. Coordinate, momentum. Coordinate, momentum. Linear coordinate, linear momentum. Angular coordinate, angular momentum. They are paired, so we say conjugate. Kinetic energy in Cartesian coordinates is expressed as 1/2 x dot squared, that is 1/2 m x1 dot squared, x2 dot squared, and x3 dot squared. This is the kinetic energy. But we can make use of conjugate momentum. Conjugate momentum, P. So x dot equals P over m. So 1/2 mx dot squared is 1/2 m P over m squared. So we can write it P squared over 2m. So this is another expression of the kinetic energy. We can either write in terms of velocity or in terms of conjugate momentum. Coriolis' work-kinetic-energy theorem is already proved. So what we have done was F equals ma, and we multiplied the velocity. We expressed in terms of acceleration that v, and use Leibniz rule to express as a differential of 1/2 mv squared and dt, and we move this one to find out f dot v dt equals differential of 1/2 mv squared. Therefore, this one became f dot dx, and we have defined this one to be work, and this one, if we integrate both sides, the difference of the kinetic energy. So this is called the Coriolis work-kinetic-energy theorem. Why don't we consider the relativistic case then? I told you F is mx double dot only for the non-relativistic case. In relativistic case, This one is not correct. Correct expression for the force is, as I stated, force is time derivative of linear momentum. And the momentum here, linear momentum is mass times the velocity. However, in Galilean relativity, m dot equals 0, and t, m dot equals 0 because m equals m prime, and t equals t prime. The time is invariant, the mass is invariant. However, this mass depends on the velocity. That's the fact. That is the consequence of the fact that we call this strength vector velocity squared over c squared square root. This is a Lorentz factor. This Lorentz factor determines time dilation. And this tau is the proper time that is for the clock that is fixed to the observer. But moving clock always dilates. All right, because of that, mass increases. If you're interested for how to derive this, you must learn y22, y23, and y24 with K-pop guide will generate physics 2. In the next semester, or just you can refer to these lectures for the speed of light until you find the 4 vector. When you understand the 4 vector, that is for the Minkowski 4 vector, mass increases. So let us assume this is a fact, then when we can compute the kinetic energy of the relativistic particle. Okay. Here, we can substitute this one in here. It's the m0 x dot square root 1 minus c squared x dot square. We compute work. Kinetic energy is the work from the state at rest to the state when the particle has the velocity, non-vanishing velocity. And F equals time derivative of momentum, and that dx, we change the variable. So this is dp dot x dot. So what you have to do is x dot dp. So x dot dp m0 x dot square root 1 minus c squared x dot square, and this differential. It looks complicated, but Leibniz rule is quite useful. Leibniz told us differential of product is differential of A times B plus A times differential of B. This is the form AdV style, and more general A dot dV style. So if I know the A dot dV, then it should be A dot B subtracted by B vector dA. Haha, this is called the integration by parts. All right. So this is this force displacement. Shifted this one to the displacement to replace it with the velocity. And velocity is copied. And total differential of momentum. Momentum has invariant quantity that is a rest mass. It's pulled out. And velocity and square root 1 minus v squared over c squared. Using integration by parts, we have a differential of this total, everything all together, everything all together. Why c squared appears? I just divided by c squared and multiplied by c squared. And then x dot d something. This is a and this is b and this is ab and dA. A little bit complicated. Actually, what should I do is this one, divided by square root. And this one can be combined. It is just a 1/2 of differential of x dot squared. And I rescale it by c squared and multiply by c squared. And then this one is a minus of c squared d 1 minus x dot squared over c squared. So this is the result. And this was the negative sign, but I have negative sign on it, negative, negative, positive. Now this is a trivial integral, and this is nothing but something like this, where x, this one can be replaced with x, and we have denominator factor of 2. That factor of 2 comes from this shift. Right, this is root x. The first integral is here. The kinetic energy is the work done by some another external force, net force on a system from the state x dot equals 0 at rest to a state with non-vanishing velocity. Therefore, this is a definite interval from x dot equals 0 from to x dot that is not equals to 0. Okay? So we should put x dot non-zero and x dot equals to. This numerator can be expressed okay. I have inserted the values, the initial point and the final point. This integral is trivial, non-zero value subtracted by the value at rest. And this one is rewritten in terms of the factor in the denominator. So I have added 1, subtracted 1, I have kept this term in here. So it gives a gamma, that is the Lorentz factor, and inverse of a Lorentz factor subtraction. The second integral is something like dx to square root. And this is the square root of x. This value, non-zero, the same value at x dot equals 0. That is 1. And this term and this term cancel exactly. And this one subtracted by 1 is the final answer up to over factor m0c squared. The kinetic energy of a particle, relativistically moving massive particle, is therefore mc squared, open the parentheses, Lagrangian factor gamma subtracted by 1. And m0 gamma is m0 square root 1 minus x dot square over c squared. This is the mass, velocity dependent mass. And mc squared subtracted by m0c squared. Kinetic energy vanishes when v equals 0 because this term becomes m0c squared. In here, a particle's energy is understood to be m0c squared plus kinetic energy. And this one is mc squared or m0 gamma c squared or m0c squared over square root 1 minus x dot square over c squared. Even in the limit as t goes to 0, particle at rest has the energy m0c squared. So that means if a mass of m0 of the rest mass disappears, we can obtain a very large amount of energy that is m0c squared because c is an enormous number. That is the source of atomic energy that is applied to nuclear power plant and atomic bomb. If you want to study further, please refer to Y22, 23, and 24 of KPOPE Guide for General Physics 2. Now, we have almost completed everything, and now we summarize what we have learned in the later part of this lecture. This is power integrated over time, then you will obtain the work. And if you compute the work done on an object, then you end up with the number that is the difference in the kinetic energy. The work is f dot dx, that is scalar product. So force and displacement and cosine theta, where theta is the angle between the force and the displacement. Unit f dx is the work. So this is a SI unit. Force has the unit Newton and meter. Newton meter is called the joule. And power, that is work per unit time, that is written in SI unit system as watt. Either watt, W-A-T-T, or capital W, that is joule per second. Exercises. This is the case. The force is applied to make a displacement of an object with an angle theta. The work done by the force is Ft cosine theta. You can consider the frictional force on this, and the resultant net force does work to an object. So net force must be computed to consider the change in the kinetic energy of a particle. So you end up with a result. If you consider a particle under a uniform circular motion, the speed is constant. As you know, the kinetic energy is 1/2 mv squared. That is independent of direction. So uniform circular motion is the speed v is constant. Therefore, on the uniform particle under a uniform circular motion has a constant kinetic energy. If I consider the Work-Kinetic-Energy Theorem, the force that makes the uniform circular motion is always heading toward the center. And displacement is perpendicular to that force. That's the reason why the work is always zero to keep the constraint that kinetic energy is constant. We remember the position vector on a circle from this measured from the center has squared value to be radius squared. That is constant. Because radius is constant, its differential is obtained by using chain rule or the Leibniz rule equals 0. It means differential of the position, that is the infinitesimal displacement, is perpendicular to the position relative to the center. This again proves that the displacement is perpendicular to the force because the force is, this is position and the force is proportional to minus position vector minus x. This is true for the case if you have magnetic force. A charged particle moving with the velocity on the magnetic field is expressed as q v cross b. And the force scalar product of the force and the displacement, you will find the v cross b and the x. Why don't we express this one, the x? We write this one as a velocity times differential of time. Then you will find that triple scalar product contains the two identical vector. So these three vectors are coplanar. It's impossible to make a volume of this triple scalar product, so it's vanished. So you can do it yourself. It is a very simple problem. Next, we consider the case. This is a pendulum moving around. The length of the pendulum is fixed, but its angle varies. This coordinate is angle coordinate. So here, and actually we need to consider the rotational version of the Newton's laws of motion. So in that case, the coordinate is theta, and the momentum is replaced with the angular momentum. And that angular momentum is the conjugate momentum of the angle. Anyway, later you will find that this problem is quite important to compute the potential energy in combination with the Work-Kinetic-Energy Theorem and the conservative force that gives the work done by that force is independent of the path, and it depends only on the initial and final position, then we say it is conservative. And if the force is conservative, then we can define the potential energy, and the sum of the potential energy and the kinetic energy is called Hamiltonian. The Hamiltonian is the total mechanical energy of the system. And in that case, the total mechanical energy of the system, or Hamiltonian, is conserved. If there is a conserved quantity, in many cases we do not have to carry out a long calculation, and immediately we can make use of the invariant quantity to find a solution for a simple problem. Anyway, to compute that potential energy, we need to compute the work done on an object due to this gravitational force. Anyway, the force applied to this object by tension is this tension is always along the string. Tension does not work at all because the displacement is the circular motion. The displacement is always perpendicular to that direction, and the force is always along this direction, and displacement is always perpendicular to that direction. So this tension does change the direction of motion, but it cannot change the energy. However, gravitational force is going down, and among the displacement in the displacement, we can decompose the displacement into two pieces. That is parallel to the gravitational force, gravitational field, and perpendicular to the gravitational field. And at the end of the day, you will find that you have to compute the parallel component of the displacement relative to the gravitational field. Then the work done by the gravitational field, gravitational force, is gravitational force multiplied by the displacement component that is parallel to this gravitational field. That is actually, this is the length L of the pendulum. The length, the position vector is here. Position vector parallel to the gravitational field is here. There's L is here, angle theta, and this position is length is L cosine theta. If the angle varies from 1 to 2, another angle theta 2, then we would have L cosine theta 2. So the displacement between these two states is this one. And mg is the force, and the displacement parallel to that force is this one. So difference of L cosine thetas is the work done by the gravitational field, gravitational force during this motion. If an object is a constraint to move along slope that is making an angle theta with the horizontal plane, again, the constraint force is, there is a gravitational force, and another constraint force is the normal force. You will find that normal force is perpendicular to the path, so it is impossible for the normal force to work on this object. So normal force is just a constraint to let it move along this slope, but normal force cannot change the kinetic energy at all, because it does not contribute any sensible work. It has a vanishing work, no work. The only force that does work on that object is a gravitational force. Again, only the parallel component among the displacement, the parallel component to the gravitational force is, because this is the angle theta, d sine theta. D sine theta is the parallel component of the displacement relative to the gravitational force. So by making use of this, you can carry out the detailed calculation for this problem. Next, we consider the work done by a restoring force, a spring, which is called the Hooke's law. Hooke's law is an approximate relation. It is not fundamental, but it is phenomenologically useful. In a relatively small range, the spring wants to restore its own shape. Let us consider the state of spring in a relaxed state. Relaxed state that is in equilibrium. Relative to this equilibrium state, if it is compressed, either compressed or dilated, the spring generates a force opposite to that displacement. So this is 0, and this is x, and opposite direction is -6. So k is a positive constant. So restoring force is proportional to the displacement from the equilibrium position, but it is opposite. We can find that F equals kx. Dimension can be computed. So it's a force and force per length. Let us compute the work done by a spring, that is minus kx, between two positions, initial position to final positions. Then, because of this negative sign, I have this, and k is constant, and we have x dot dx. We know this one very well. This is 1/2 of x squared is the differential. So that is a minus due to the sign of the restoring force. And then so we substitute the final state and initial state. 1/2 kx squared difference. Do it yourself. In case we have the force depending on x, just like restoring force, this one becomes the area under the curve in the one-dimensional case. If f is here, x is here. In three-dimensional case, you can compute the components f1 dx1, f2 dx2, and f3 dx3 separately integrate. Or by chance, we can find the total differential, so something like kx squared in the previous case, because it was x dot dx style, then we can directly integrate. The application of the damping force can be considered. We have solved this problem previously, so let me pass it. If there is a power depending on time, the work done on system can be computed as a power as a time integral. All right. These are the application of the restoring force. A block of mass m falls into a relaxed vertical spring with a spring constant k. The block lies massless plate A attached to a spring and stops at point B. All right. you need to find the work done by the gravitational force from here to there first. Then you will find the velocity of the particle because the work-kinetic-energy theorem will give the final velocity just before it touches A. And then you go further. The gravitational force does work further to approach here. However, the restoring force of the spring does work in the negative sense. You will find that this, because it stops in here, the total kinetic energy of the particle will be zero at point B. Using this condition, you will find the final result. Okay, this is the last part, self-test. We are now familiar with the Leibniz rule for the differentiation of product function. Without this, our life is a very uneasy, and due to that formula is is very convenient to derive. It was very convenient to derive the work-kinetic-energy theorem. To us, it was very easy to derive because everything is known right now. However, even Leibniz was not able to find out the missing factor 1/2, even though he developed that formula. He was not stupid. Once the answer is known, copying the result is very easy. But anyone who develops something new, it is very, very difficult. So you should be very thankful to them who have developed this all of the tools. And these tools are not developed by mathematicians, it's mostly developed by physicists. Please remember, mathematicians copy all of this physics result in the textbook, and in the first part of their textbook, they say they have, just like that, they don't really say, but they pretend that they have developed everything, and then at the end of the textbook, they usually write it as an application of mathematics. But it is not an application of mathematics, it is physics. To find the solution of physics problem, they have developed all of these kind of formulas. Please remember, please remember. Okay, so we know how to take the derivative of the product A prime, B, AB prime. And it was quite useful to find what? Find the integral. A prime B integral. How can I do that? So AB prime in prime and subtracted by AB prime. That's it. So this is called integration by part, and we just have made use of this formula to find the very famous formula of mc squared minus m0c squared is the kinetic energy. To this, mc squared is the kinetic equals the kinetic energy m0c squared. And what is that? The rest energy of the particle, even though there is no motion at a particle at rest, the kinetic energy vanishes, still there is an energy m0c squared that is the enormous amount of energy that produced many, many things. Anyway, just like that, to solve the physics problem, we will encounter a similar problem or more complicated problem that can be derived by making use of mathematical induction. Just use it repeatedly. How?
consider ABC prime. What should I do? Oh, replace this AB as X, then XC prime. Oh, I know how to do that. And then substitute X equals AB. Then, oh, AB prime C plus AB C prime. Oh, I can expand this. A prime B plus B prime A C. That's it. Okay, what's the answer? A prime B C. A B prime C. And A B C prime. Okay, that's it. However, this is simple. This is just the single derivative. What happens to you if you have n derivative? Oh, it's a headache. Before doing that, first carry out this step repeatedly. You will find if there is a single derivative, you will find it is a1 to an. For example, AB prime is A prime B and AB prime. Why don't you divide everything with AB? Then you will find this A prime over A and B cancel. B prime over B. Oh, it seems symmetric. It seems symmetric. After I will obtain this AB prime equals AB times A prime over A and B prime over B. Expand. Then BA prime, AB prime. What's next? ABC prime. ABC. It should be A prime A, B prime B, and C prime C. Multiply ABC prime equals A prime, BC, B prime, CA, and C prime, AB. Oh, that's the relation. And then, why don't we repeat this derivative many more times. But then it becomes a problem of combinatory. I'd like to take the derivative. Then there are many vectors, and I can distribute these derivatives into many pieces. dt over d, d over dt, d over dt, d over dt, and d over dt. And the number of derivatives will be n, so let me choose n k1, k2, k3, and kn. Then we have a1, a2, a3, blah blah blah, an. And number of derivatives will be the same, so I have a constraint capital N. It should be the same as the sum of k's. Using this way, I can do the differentiation. However, there is a multiplicity. How can I distribute n derivatives to n vectors? Once it is located a single one, I cannot distinguish the order of the k1 derivatives. Therefore, I have a permutation of a total number of derivatives, and because these are identical, and these are identical derivatives, so this one is called a multinomial factor. Coefficient. The similar true, very similar general and the generalization of the binomial coefficient. We are familiar with this n factorial, k factorial, n minus k factorial. Okay, when you expand a plus b to the nth power, this binomial factor coefficient appears. Okay, using this way, why don't you prove this theorem for the derivative, nth order derivative of a product function, most general case, then you can carry out any kind of uh, product function. And because I have already explained too much detail about the calculation of kinetic energy in the relativistic case, let me stop here. And finally, the Euler's number E is quite important, and the mathematical definition of the Euler's number appears here. And actually, you can add additional p's of higher orders in the nth square or cube and further. However, if you take into account expansion in powers of n and take the limit n goes to infinity, all of the contribution for the higher ordering 1 over n and power vanishes exactly. It is not an approximation, it vanishes exactly. That's the reason why we have a very simple formula for the derivative of exponential function, and its inverse, uh, log. Okay, that's it for today.